Okay, in this video we're going to learn about two-dimensional numerical integration, and what I'll do is first give you an overview of how this works, and then we'll look at an application that uses an Excel worksheet. So let's start off and go back to one of the examples that we worked in class. And in this case, we did the integral from 0 to 4 of the square root of x. And we used these different methods. This is just a 1D integral, a definite integral over these limits. And so the way that we did it was we said, well, x is going to vary from 0 to 4. And so we said, well, x is going to start here and end there. And I need some intermediate values. So we have x. In this case, we just had a delta x of equal to 1, and so we ended up with 5 values between 0 and 4. And then we evaluated the function, which is square root of x, at each value of x. We got those values. And then to do the integration, we used the trapezoid method first, and we recall that the trapezoid method was the summation of these terms. And so for I equals 1, we could go and calculate that out, and that was this plus this times that minus that, and that gives us that value. And then for I equals 2, we had this value, and so on. So these are the terms in the series that we'll then add up to get the integral here. And I think at some point, yeah, it looks like what we did here was this 1/2 really came inside here. So each term was the average times the delta x. Okay, so the midpoint, we did the same thing. We had some individual terms that we added up to get the integral. All right, so now we want to go and do this in 2D. So let's take a look at this particular integral here. We're going to integrate this function between these limits. The integral from with respect to x is taken from 100 to 200, and from y it's 50 to 330, because the dx is here, so we have this block being one integral, and then that's embedded within this other integral that's with respect to y and over these limits. Okay, so we can write this in a discrete form where these integrals are written as summations, and we go just in kind of a generic way. We're summing using the index I and j, and in this case we have the discrete values of x and y, and we're evaluating the function at those values, and we have some weighting function here. And so we evaluate the function at each point, and what we do is we first of all, for j equals 1, then we go through the whole cycle from I equals 1 to n, and we evaluate the function and the weighting function, and we add it all up. And for j equals 1, we end up with a value that is this summation. So if we think of these as the indices here, and if this is j, then for j equals 1, then we do the summation. And what I'm thinking of here is that each one of these gray boxes has the value of this function determined at that location. So I filled in some hypothetical numbers right here. Each one of these boxes would have a number that's this function evaluated at that location. So what this says to do is for j equals 1, we go and we take each value of the function for these different values of I, and we do the summation for different weighting factors, and we would sum across like that and put the result right there. Now, the actual way that we would do this summation depends on the particular method of integration that we're using. Could be the trapezoid or Simpson, or it could be the midpoint method. Okay, so that's the first step. And then we go and we repeat that, because the next time j will equal 2. And we go on and we add up all of these guys. And so we end up with a value for each one of these summations going across the row. Okay? Then what we do is we need to integrate with respect to j, and so we're going to essentially just do the summation along these intermediate values, and that will give us the result here. Okay, so we end up with this double summation kind of visualized in this way, and actually, as we'll see in just a second, it's more than just a visualization. So let's turn to Excel and see how we might implement this. So there's a worksheet where I'm going through this procedure. Let me see. It's called Double Integration Example. So you could open it up if you like. And this is doing the integral that we just saw using a couple of different methods. So first of all, here's the function up here. And that's just a text string. We have the exact value here that I worked out using Scientific Notebook. We could work it out by hand, but I just checked it in the Scientific Notebook. And then I have the limits here, the lower limit and upper limit of x and y. And what I'm given, or what I'm assuming, is that there are 10 points along x and y. So if we have 10 points, then our delta x is given here. This is the upper x minus the lower x, the total interval of x divided by the number of points minus 1. And so that's delta x, and we have a similar expression for delta y. So here's my grid, and this is what I'll use to do the integration. And the way I have this laid out is this is the x-axis, and this is the y-axis. And so I start here at x equals 100, and then the next column here is 100 plus delta x, and so on. This is this column plus delta x, and we go up to 200. And then y is done the same way. There's the lower value of y and that value plus delta x. And so we set this up with these functions and with these variable names, and this is nice because it allows us to change this without really making any changes in the code. We could, for example, change the upper limit of y to 350, and if I do that, everything changes and the result changes. So this gives us, this way of doing it gives us a lot of flexibility. Okay, so now we have each interval here partitioned the way that we want it, with equal values, or even values of equal values of delta x and delta y. Now, for the midpoint method, what we need is to evaluate the function midway between these points. So I set up this column here, the yellow column, and in that cell, that's midway, the average, between these two cells. Just write that average there, and then I just copied this down. So each cell here is the average of these two. And this yellow row is the same thing. It's the average of these two written here. Now what I can do in the gray box is evaluate the function right here at that value of x and that value of y. And here's the way to do it. I wrote a Visual Basic function called Integrand, An integrand is a function of these two parameters, and they're the value of x right there and the value of y. So I could, of course, just written this function out within the worksheet, but here's kind of a nice feature. Since I made this a function, I can go here to Visual Basic, and there's the function integrand, and we see the function there that we saw earlier on the PowerPoint. And one thing that's kind of handy is if I wanted to integrate another function, I could just put that function right here and everything else would work back on the worksheet. So again, it just gives us a little more flexibility. So the midpoint method tells us to sum these values multiplied by delta y, and then we get this value. So this is the sum of all of these values. So this is like that first step of integration along this. In this case, it's a column. In the PowerPoint example, we saw that it was a row, but no big deal. This is the intermediate value, and we do that for each one of these columns. And then we get these intermediate values, and down here, this is the sum of this row. So this is the integration with respect to, this is integrating essentially with respect to x. So each one of these integrates with respect to y, and then with respect to x. This is then the intermediate value. We've just added up, though. We still have to multiply by delta x and delta y. So right here, it's that sum by delta x and delta y. Okay, so pretty straightforward, I think, hopefully. And then I want to calculate the error. So this is the relative error, the exact value that we have up here, minus the approximate value divided by the exact value. And you can see that the exact value is 5486. This is 5508, so it's pretty close. And you can see the error is less than 0.5%. So quite good in this case. Okay, so that's the midpoint method. Let's take a look at the trapezoid method. This part of the layout for the trapezoid method is really the same as what we have here. Well, it's actually a little bit different, but similar conceptually. This is x partitioned up and y partitioned up. And what we've done in this case is to evaluate the integrand at that value of x and that value of y. And so instead of evaluating it at the midpoint, we're evaluating it at these points per se. So for the trapezoid, in order to do it on a worksheet, we really need an intermediate value. And this value here is the average of those two values. And this one is the average of the next two, and so on. So now we go down here, and this is the sum of this column. And so in this case, the trapezoid method, it's the average of the values of the integrand times the value of delta x. Well, in this case, we set it up so delta x is the same everywhere. And so we don't really need to multiply by delta x in each term. What we'll do is evaluate the terms in the series. This is one of the terms, and then we add them up here. We do that for each column. And then what we do to integrate along the row is we take these intermediate values, and right there, that is the average of these two. And we calculate the average of each one of these two. And then we sum this whole row, and that sum is right there. So we factored out delta x and delta y from this, and so just like for the midpoint method, we have to go and multiply by delta x and delta y when we're done. And we do that, and we get this value, and you can see in this case we have a 0.8% error. So a little bit more than the midpoint method, but still really remarkably close. Okay, so now we are going to want to do the trapezoid method by rows. What we did previously was to take the average of these two and write it there. But now we go and take the average of these two and write it there. When we did this previously, we were left with a blank row here. And so now when we're doing this with respect to the rows, we have a blank column. Okay, so this is the average of those two. This is the average of these two, and so on. And then once we have these worked out, we go and sum across the rows, and we get that value. And we do that for each one of the rows. And then the trapezoid method, it always involves this average. So when we go and integrate with respect to y, just like we did previously, we're going to make an intermediate column, and this is calculating the average of those two, and so on. And then we add that up, and that's the value that we need to then multiply by del x and del y. And lo and behold, look at that, 5442.2004. So it's pretty cool. We get the exact same result if we integrate doing this by rows, or doing this by columns and then by rows, or the other way around. You get the same result. And it still is quite close. All right, so now let's go and do the Simpson method. And we need to have a odd number of points. So we've changed it around a little bit. Here we had 10 points, and now we go and use 9 points. So we're going to recalculate the delta x and delta y, and here they are. So it still is the same. This value is that value plus del x Simpson. And so this gray box is the same as the gray box here. Well, except the points are different. But essentially what we're doing is the same. We take the integrand, we evaluate it at that value of x, that value of y. This guy right here is the integrand evaluated at that value of x and that value of y. Okay, now we have to construct the term in the Simpson series. And so let's go right here. And the term that we need to calculate here is, let's go and see how it's working. So we're going to be integrating along the column, and this term here is 4 times that value plus that value plus that value. We write that term there. In the past, when we've done this, we've taken this same calculation and written it right there. I think that's how we did it when we did this Simpson method by hand. It doesn't really matter which one of these cells you write it in, but the point is that we're going to take this group of 3 and write it in one of these cells, and then we'll take the next group of 3 where we've used this one twice. We use it during the first group of 3, and then we'll use it during this next group of 3, and we write the intermediate value there, and then the intermediate value there, and so on. Then we go and sum it up, and in this case what I've done is I've summed it up and I multiply by del y, then divide by 3. So this is the full integration with respect to y. And then I do that each time, all along. And then I need to integrate with respect to x. And so the procedure is the same. We have this intermediate row, and the term right here is this plus that times plus 4 times that, and we get 4 of these, and we add them up, and we get that value. And what we're doing is here adding them up, and then multiply by del x, Simpson, and divide by 3. So we then do a check, and here's the result. We do the relative error, and this has 5.5 or 0.5% error. So all of these have pretty small amount of error, less than 1%, and so that's going to make it really quite useful for a variety of applications. And in this case, this midpoint method, probably the simplest of all of them, has the lowest error. That won't necessarily always be the case, but in this example, it is. So there are these 3 different examples. I guess we could also do Simpson method going in this direction, but I'll leave that to you to work out on your spare time. Perhaps when you're on vacation, you can work the Simpson method going the other direction. So good luck. I'll want you to work out an example of this on your own, and there'll also be a homework assignment. Those will be described in another video.